So the Professor Tartarone,
Okay,
do you hear me? Welcome,
Yes,
sir.
yes. Can you hear me?
Yes,
Okay.
yes, we can. So are you ready?
Okay. Yes, I can hear you. I will. Okay, I'm trying to share my screen,
okay.
but I think Professor Kim should.
Okay, yeah.
Okay, yes.
Sorry.
Okay. Wow. Okay.
Okay.
Can you see?
Yes, yes.
Okay.
So the next presentation is from Professor Tartarone, that we would like to thank for being with us today in this event. So her presentation is titled Prufer-like properties for integer-valued polynomial rings. You have 13 minutes. The floor is yours.
Okay. Thank you very much. First of all, I would like to thank the organizers for this very nice conference, and I'm honored to participate to a conference for young people, even if I'm not so young anymore. And I also would like to share a little thought for Professor Zafrullah, who I met many times in some conferences, also in some conferences in Italy that I organized many years ago. And I have always been working in the field of multiplicative ideal theory. And so I read a lot of his papers, and I emailed with him many times, even though we have never worked together. But I can say that his work really much influenced my work, and I think also the research of many of my colleagues. So I thank him for his research. And I also would like to say that I had the opportunity to talk with him, even if I didn't smoke, never, but we found some moments to talk about mathematics. So my talk is a kind of survey, but not only a survey. At the end of my talk, there will be also some spreads of new results that I'm working on with Alita Musi. And so I will start with the Prufer domains and then switch to PVMD domains, which are a sort of Prufer domains for the T operation. And all my talk is focused on integer valued polynomials. And so when the integer valued polynomial ring has these properties, Prufer, but especially PVMD. So first start with the Prufer notion, which is a natural globalization of the concept of valuation domain. And it was introduced by Prufer in 1932. The main definition is that a domain is a Prufer if its localizations at prime ideals are valuation domains. But equivalently, we can say that a domain is Prufer if every finitely generated ideal is invertible. And in fact, we have that Dedekind domains are exactly the Prufer Noetherian domains. In fact, Dedekind domains are exactly domains in which every ideal is invertible and they are Noetherian. But there are many interesting examples of Prufer non-Noetherian domains, and one of it is given by the integer valued polynomial ring over the integer int z, which is the set of polynomials in Q bracket x, which sends the integers into the integers. Because in fact, in general, the ring d bracket x or z bracket x is not Prufer unless d is a field. So if we think about z of x, this is not Prufer, but it is contained in int Z, and int Z is Prufer. Obviously, this is Prufer because Q is a field. And so generally, somebody already, also Ali, I remember yesterday, Talita Mussi introduced the integer valued polynomial ring over a domain D. So this is a generalization of int Z. So int D is the set of polynomials with coefficient in K, where K is the ring of fraction of D, which sends D into D. And as I said before, in general, D bracket X is never Prufer unless D is a field. A complete characterization of integer valued polynomial rings that are Prufer was given by Alan Loper in 1998, but he arrived to this characterization after a long research in this topic. Many researchers, Cahen, Chabert, also Robert Gilmer, studied the problem of the Pruferianity of int D in the past, and so they have been found some partial and also interesting results that then brought to the general characterization found by Loper. And it's interesting, the Noetherian characterization of when int D is Prufer. So when D is Noetherian, int D is Prufer if and only if D is Dedekind with all finite resolute fields. So Z is one of these examples. And this theorem was found many years before Loper by Cahen and Chabert. It's important, this hypothesis, because when we remove this hypothesis, so we ask only that D is Dedekind, we will see that we'll obtain an analogous characterization, but for PVMD. So I give some notion about the T operation, even though this notion have been recalled by Professor Kim before me and Dr. Tamoussi before me yesterday. The T closure. The T closure is a closure operation on ideals, which is constructed by considering finitely generated V ideals. So if we have a fractional ideal I of D, the T closure of I is the union of the divisorial closure of the finitely generated ideals contained into I. An ideal is T ideal if I is closed under the T operation. The V closure is exactly this one. Professor Kim introduced it in the talk before mine. And what it is interesting about T ideals is that the set of T ideals in some sense has the main properties of the set of ideals in a domain. That is, there are T maximal ideals always, and usually, and with the V operation, this is not true. And each T maximal ideal is T prime, which means that it is a T ideal which is also prime. And each T ideal is contained in a T maximal ideal. I also will add that every domain D can be written as the intersection of its localization at T maximal ideal. So the T operation works very well in multiplicative ideal theory. In some sense, it is better than the V operation, even if it comes from there. And so we have a generalization of the Prufer domain using the set of T ideals and not the set of all the ideals of a domain D. So we say that an integral domain is a Prufer V multiplication domain, PVMD, if dP, so its localization at P, is evaluation domain for each T prime or T maximal ideal. And analogously, as for Prufer domains, we said that the Prufer domain D is a Prufer if and only if also every finitely generated ideal is invertible. Here there is also an analogous for PVMD. PVMD is equivalent to say that every T finite ideal is T invertible, but I don't want to go in deep into these concepts because it will take too much time, and I would like to focus on other problems, on other questions. So the notion of PVMD was introduced by Griffin during the 60s, but then it was also studied by Mott and Muhammad Zafrullah in 1982 in a very interesting paper that I used a lot of times in my research. And PVMDs are strictly, it's a class of domains strictly larger than Prufer domains, because, for instance, integrally closed domains of dimension greater than 1 are PVMD, but they are not Prufer. And PVMD are also central in the theory of divisibility of integral domains, because, in fact, GCD domains, domains with great common divisor, are exactly the domains which are PVMD with a trivial T-class group. The T-class group is a generalization of the class group of a domain, restricting only to T invertible ideals. And besides the Prufer domains, other examples of PVMDs are exactly the Krull domains and also polynomial rings over PVMDs. So in this case, we have that if D is a PVMD, D bracket X is again a PVMD. This fact, we know that it is not true for Prufer domains. So many years ago, when I started to work on these domains, I found that if D is a Noetherian domain, then int D is a PVMD if and only if D is Dedekind. So this is a generalization of Cahen-Chabert theorem about Pruferianity, because just relating the hypothesis that D is with finite residue field, so D is only Dedekind, then we have that int D is not Prufer, but it is PVMD. And so I focused for many years on the problem of characterizing domains D for which int D is a PVMD. I just recall which are polynomial primes and interprimes of a domain D. We have a general domain D, and we can consider two subsets of prime ideals of D. The polynomial primes, which are the primes for which, when we localize int at D minus P, we get exactly the polynomial ring dp bracket X, dp bracket X. These are called polynomial primes exactly because the localization of int D at these primes gives a polynomial ring. And these are good primes. I mean, these are primes with which we know how to deal with, because the prime ideals of int D, which contracts over these primes, comes from prime ideals of dp bracket X. So in some sense, we know how they are done. Then we have the int primes. The int primes are exactly the other primes. So the primes for which we don't have this equality, but int D is not contained in dp bracket X, and necessarily these are maximal with finite residue field. Once we have done this distinction, then we have two subsets, delta 0 and delta 1, set of the int prime and set of the polynomial primes. Then we can consider these two overrings of D, D0, which is the intersection of D at localization at int primes, and D1, which is the intersection of D at polynomial primes. And so we have the D, that D is the intersection of D0 with D1. Int D, it can be shown that int D is this intersection, and this is interesting because in this way we have a non-polynomial part of int D, which is int D0, and we have a polynomial part of int D, which is D1 bracket X. And so then we focus on these two rings separately. The general characterization of domains D such that int D is a PVMD is the following. This was given by Cahen, Loper, and Dhar many years ago, and it states that if D is any domain, then int D is a PVMD if and only if the following conditions hold. First, D should be PVMD. Second condition, each int prime, I recall that these are the int primes, so these are the primes which don't lead int D to be polynomial ring in some sense. This should be high to 1. And the third condition is a kind of condition of separability between delta 0 and delta 1. This says that each p in delta 1 should contain a finitely generated ideal which is not contained in any prime in delta 0. This is a very technical condition, but if you go deep into the proof of this theorem, you will see that it's really, it's really very important, and it is the condition that makes the difference between the Noetherian case and the non-Noetherian case. So, we have seen that int D is the intersection of these two overrings, int D0 and D1 bracket X. And if D is a PVMD, then it is known that also D1 is a PVMD, and so D1 bracket X is PVMD. So what happens to int D0? What we showed is that if int D is a PVMD, then its pure integer valued part, not polynomial part, is Prufer. So if int D is a PVMD, we have that this is D bracket X is a PVMD, but these over rings is exactly Prufer. And unfortunately, this condition is not sufficient to get that int D is a PVMD. I mean, if we suppose that int D0 is Prufer, we cannot, also assuming that D is a PVMD, we cannot have that int D is a PVMD. So it is a necessary condition, but is not sufficient. And we also gave an example of this fact on the same paper in which we proved the general characterization of int D PVMD. And we constructed a suitable almost Dedekind domain to show that this condition of about int D0 is not sufficient. Connected with the concept of PVMD is the concept of cruel type domain. What is a cruel type domain? It's a domain which is an intersection of some localizations of D at primes, which are valuation domains. And we also want that this intersection is locally finite, which means that each non-zero element of D is contained in only finitely many primes that appears in this intersection. For instance, cruel domains are cruel type, and a domain has the T-finite character if each non-zero element X in D belongs to finitely many T-maximo ideals. So we have that Griffin showed that this type of domains, the cruel type domains, are exactly the PVMD with a T-finite character. In general, PVMD may not have the T-finite character. For instance, int Z is Prufer, so it is a PVMD, but it is not. It does not have the T-finite character. It's quite easy to show. So, I mean, cruel type domains are a particular type of PVMDs. And what I show with Ali Tamoussi recently in a paper that is going to appear is that int D is cruel type if and only if D is cruel type and int D is equal to D bracket X. So while in general we have a characterization that tell us that int D can be PVMD without being D bracket X. This is the characterization given by Cahen, Loper, and I many years ago. If we restrict ourselves to the case of PVMD with T-finite character, so to the case of cruel type domains, then we don't have integer valued polynomials which are not trivial with this property. And in fact, the theorem, so I mean, and also with Alita Musi, we found a lot of other domains with some cruel-like properties for which we have that int D has these properties if and only if int D is equal to D bracket X. Now go back to the main generalization. The generalization, theorem 1, I recall you, is this one, is the main generalization of PVMDs. And this theorem is also a generalization of this other result about cruel type domains. This is also a result that I proved many years ago. If D is a cruel type domain, so we assume that D is a PVMD with a T-finite character, then int D is a PVMD if and only if all the int primes have height 1. So what we have is that if we restrict ourselves to the cruel type condition, we don't need this third condition in the characterization of int D with this property. So if here we put, sorry, there is something. Okay, I don't know what happens. So what we have is that for the PVMD with T-finite character, the characterization of int D with this property is very easy, and it does not need the condition C of theorem 1. And also, the theorem above can be easily converted to this other characterization that I found with Professor Finocchiaro. Suppose that D is a cruel type domain, then we have that int D is a PVMD if and only if int D0 is Prufer. So this condition becomes also sufficient if we suppose that D is not general PVMD, but it is a cruel type domain. So it is a PVMD with the T-finite character. What it is really used to prove this theorem is not really the fact that D is cruel type, but is this equality. This means that int D behaves well under localization if we take the T maximal ideals. This is guaranteed if D is cruel type. I mean, if D is cruel type, we have that this condition holds. But this is the really reason for which the theorem works. So we have generalized theorem 2, removing the condition cruel type and replacing it by the more general condition that int D behaves well under localization for T maximal ideals. And here we have the theorem in which we can say that if int D behaves well under localization for T maximal ideal, then int D is a PVMD if and only if D is a PVMD and int 0 is a Prufer domain. A domain is PVMDs are a particular case of essential domains, or also Prufer domains, also Krull domains. What is an essential domain? Is a domain which is an intersection of its localizations, and these localizations are valuation rings. So in general, as I said before, any domain D can be represented as intersection of its localization at T maximal ideal. A PVMD is always essential because DP is a valuation domain for each T maximal ideal. And there exist also essential domains that are not PVMD. So the essential domains are a class of domains strictly larger than PVMDs. An example of this type was given by Heinzer and Ohm many years ago, and it was very technical, this example. Using the integer valued polynomial rings and the theorem 1, the theorem of the general characterization of when int D is a PVMD, with Kain and Loper, we could construct an essential domain which is not PVMD. So in particular, we construct an integer valued polynomial rings where D is an almost Dedekind domain, and in this case we could show that this is not the PVMD, but it is essential. With Alita Mussi, we showed also that if D is a PVMD, then int D is an essential domain. And this is interesting because essential domains are essential domain is the mother of all these kind of domains that I studied in the last 20 years. So PVMDs, Prufer, Krull, Dedekind, everything is an essential domains. So it was interesting for me when Alita Mussi proposed me to work on when int D is an essential domain. And soon we found that supposing that this is PVMD, then we have this property for int D. Now, I don't go deep in the proof of this factor because I see that I don't have much time, but I would like to go to the question. The question, so in general, essential domains are more general than PVMDs. So the question is, are there interesting extra conditions for essential domain to be a PVMD? I mean, if D is an essential domain, what other condition I have to put on D in order to have that this is a PVMD? And so here I worked on this question with Professor Carmelo Finocchiaro, and we used some topological tools. Especially we worked with ultrafilter. Here I may try to give you in very synthetic way some basic notions about ultrafilter. So you have the definition of an ultrafilter over a non-empty set X. This is a collection of subsets which verifies this condition 1, 2, 3, and 4. And in our work was important also to consider principal ultrafilters, which are ultrafilters for which there is an element which is contained in every set of the ultrafilter. And what we can do with ultrafilters is to construct limits of ideals. I mean, suppose that you have a family of ideals of a ring A, and for each X in A, you can consider these sets Bx, which are all the ideals of the set X, such that little x is in A. And if U is an ultrafilter over this set of ideals, then we can construct an ideal XU. This is an ideal, which is called the ultrafilter limit of the family with respect to U. More explicitly, this ideal is constructed in this way, if you want to see it in a more, some more algebraic way. And if you use a principal ultrafilter, then you have that exactly XU is equal to the ideal I that is contained in every set of the ultrafilter. So, but what it is interesting is that well, first, no, I go back 1 minute. If you have that, for instance, if you have that the family is made of prime ideals, the family is made of prime ideals, then sorry, the family X, not UX. Okay. Then the limit is a prime ideal. And if the family is made of T ideals, then you have that the limit is a T ideal. Suppose that Y is an unempty subset of the spectrum of A and U is an ultrafilter on Y, then the limit is a prime ideal called the ultrafilter limit point of Y. And we say that Y is closed under ultrafilters if Y contains all its ultrafilter limits. And this is its closure. This is its closure under the ultrafilter topology. For example, I don't go into the proof, but if you take the maximal ideal of Z as the set Y, you can easily see that it is not closed under ultrafilter because all the non-principal ultrafilter limits are 0. And so with Carmelo Finocchiaro, we could give a characterization of PVMD using ultrafilters as follows. Suppose that it is an integral domain and consider gamma D, the set of the primes of D such that DP is evaluation domain. Then the following conditions are equivalent. D is a PVMD. D is an essential domain with a representation, D intersection of DP, where Y is closed, like the closure of Y under ultrafilters should be contained in gamma D. So the extra condition that we have to put on an essential domain in order to get that D is a PVMD can be a topology, a kind of topological condition using the ultrafilter limits. If D is a proofer, then this theorem is trivially verified because for every prime ideal, DP is evaluation domain. So for proofer domains, gamma D is exactly the spec of D. And so it's obvious that the ultrafilter limit, which is prime, is contained there. This condition is guaranteed in theorem 1, I mean, in the general characterization of when int D is a PVMD by point C. So the point C of theorem 1 is a condition that guarantees this condition that the ultrafilter closure of Y is contained in gamma D. And just I just go very fast on this because I just wanted to recall also Muhammad Zafrullah in this other occasion of my research when I started to work with Halita Moussi on essential domains. We really wanted to find the characterization of when int D is locally essential. And also this definition of a locally essential domain comes from a paper by Motta and Zafrullah, the same paper that I cited at the beginning of the talk. And in this paper, they gave very interesting results about PVMD, but also about these P domains. They call these P domains, which are domains such that DP is evaluation domain for every associated prime. And then these are also called the locally essential domain because then they showed that this notion of P domain was equivalent to ask that each localization of D is an essential domain. And with Ali, we we worked about this notion for int d. These are results contained in a paper that we submitted, but the main reason for which I wanted at the end of this paper, this talk, to introduce this notion was also to recall also Zafrullah. Then here, I mean, these are two results that we found, but it will be needed another talk to talk about that in a very clear and exhaustive way. So I just finish with some papers that I used in this talk. And the last paper is a paper submitted, and here you can find this is the paper about I talked in the last slides. So I don't know. I think that the time is over. So I thank you again for the invitation and for the nice conference that you have organized.
Thank you very much, Professor. So are there any questions?
Yeah, I have a question. Can you hear me?
Yes.
Yes, sir. Yes, Professor.
First, thank you, Francesca, for this nice talk. And it's good to see you.
Yes.
Maybe the last time I saw you was in Cortona a long time ago.
Yes, I also looked for some pictures of Cortona because you made a lot of pictures. I was looking also for a picture of Mohammed, but I didn't find it.
Well, yeah, I'm famous with taking so many pictures.
Yes.
I think, you know, anyway, but really nice to see you, and thank you for a very nice talk.
Thanks, Simon. I hope to see you soon in some other conferences.
Me too. Thank you.
Thank you, Professor Badawi. Is there any questions?
Yes, I have a question. Do you hear me?
Yes.
Yes.
I would like to thank Professor Francesca for this amazing presentation. I'm so far from this domain of research, but there is something that attracted me in your presentation, that is the set int of D. This that is the set of polynomial such that if D is in D, int of D.
Yes, yes, in integer value polynomial ring.
I don't know if this set represents something, for example, because I see a lot of researchers interested in this set. I don't know if there is something, for example, if it represents something, for example, me, I see it like just a polynomial such that let D invariant. For example, if this set, for example, represents something geometric.
I don't know. I never looked for this connection with the geometry, really. So, but if you are interested in this ring and you want just to have a general look to the theory on this ring, there is a book that Caen and Chabert wrote many years ago. If you write to me, I can give you, I mean, the title, some more precise coordinates, and I mean, even this book was written around 1905, 1906, but it's very actual because they worked a lot on integer value polynomials. I can say that they were really the integer value polynomial men for some years. So I think that maybe there you can try to find something more particular. personally, I have never worked on this connection with geometry.
Okay, thank you so much.
You're welcome.
Thank you very much. Other questions?
Yes, please. I have two questions.
Yes, sir.
First of all, thank you, Professor Francesca, for this excellent talk.
Thank you.
So the first question is there any characterization of T-maximal or T-prime ideals of entity?
No, because unfortunately, we don't have even a characterization of maximal ideals of int D in general. The main problem for int D is that we don't know the spectrum, the prime spectrum, unless for some cases that have already been studied, like for Dedekind domains, valuation domains, only for some specific cases. In general, it is even unknown which is the cruel dimension of int D. There is an open conjecture which says that maybe the cruel dimension of int D is less or equal the cruel dimension of D bracket X or not. I think that nobody worked on this conjecture for many years. So no. It's a very difficult question.
Okay. So we know that cruel types domains are PVMDs. So my question is it possible to construct a PVMD that is not cruel type using
Yes, because if you construct an int D which is not the polynomial ring D bracket X, and in the paper with the Loper and Ken, we constructed a lot of these domains. You can use the characterization that I gave in theorem 1, but you can construct them with using some suitable almost Dedekind domains. Then in that case, if int D is not D bracket X, it is not cruel type, because with Alita Musi we showed that okay, I don't find it, but we showed that int D is cruel type if and only if int D is equal to D bracket here. You see? So if it is not a D bracket X, but it is PVMD, then it is a PVMD that it is not cruel type.
Yes. Okay, thank you very much, Professor.
You're welcome.
Okay, thank you. Other questions? No questions? So thank you very much for being here with us, Professor Tartarone, in this event. Thank you. So according to the program, we are going to take a short break of 20 minutes. Then we will come back to continue. Thank you very much and see you soon.
See you soon. Thank you.